Hello and welcome to Solving Trig Equations Algebraically, Part 2. I've got an example up right here, and we're going to try to solve this thing, and we're going to try to give the general solution. And the biggest difference between this and a previous example that I did is that the period of this graph has been tweaked. So I'm going to show you my strategy for solving those kinds of questions. First thing I want to do here is I want to isolate the tan 2x. So I want to just divide both sides by 3. Okay, so once I get to the point where I have isolated the trig function, I kind of ignore the 2 that's in there. I kind of treat it like this and say, well, how would I solve an equation like this? What would I do if I had tan of something equals 1/3? Well, typically, I look at the number on the right, the 1/3, and I ask myself, is this thing from a special triangle? Is there any sort of nifty way I could use a special triangle with this 1/3? And although it looks tempting, the answer is actually no. We have a √3 and a 1, but we don't have a 1 and a 3. So actually, it doesn't work. So what do I do in a case like this when the special triangle stuff doesn't work? I just hit tan inverse on both sides and make sure you're in radians. Typically, radians are going to be the default at this level of math. So now I do a tan inverse of 1/3. And so now I just see what the calculator spits out. Now the calculator, I went ahead and did this. It spat out 0.32. So I go, hey, perfect. There's one of my answers. The only problem with that is, remember, we still have a 2x to consider. You know, all we did was solve for the little, what if it was tan of something equals 1/3. So that's where we got the 0.32. I'm now going to give a general solution on that. The general solution looks like this: 0.32 plus multiples of pi. Now, the reason I can only do pi is because this is tangent. Remember, the period of tangent is pi. So once you get your one basic angle, you just have to say, yeah, plus multiples of pi, and then we've got it all set up. Now, here's the thing. This is not my final answer. This was the answer for this trig equation here. What I now have to do is adjust it. Okay, so I'm going to take the whole thing, my answer here, and I'm going to say, what effect does this 2 in front of the x do? Well, anytime you have a number in front of the x, inside your trig function, remember, we took the reciprocal. So we would take 1/2 and times the normal period by that 1/2. What that does is it squishes all of it together. So I'm going to take my answer here and squish it by 1/2. And that's all you got to do. You just do a final adjustment for this squishing or expanding to what your answer would have been. So here's what my actual answer now is. So when I've done that, I got 0.16 plus multiples of, and don't forget to multiply the 1/2 by the n pi, so it's multiples of pi by 2. So this is my final answer. Okay, there's my general solution, and I have taken this 2 into account. Whoops, I messed it up there. All right, so that is now completed. All right, let's do one more of those, and then we're probably good with this. In the second example, let's say you had something like this. 3 times cosecant x equals -9. Now, this one doesn't have a change in the period, but what do you do with a cosecant? Well, let's first of all isolate the trig function. So let's divide both sides by 3. Okay. Now at this stage, I'm going to switch out cosecant with 1/sine, because after all, it's exactly the same thing as 1/sine. And on this side, I'm just going to leave it as -3, but I'm going to write it as over 1. Now what I'm going to do is I'm going to flip both sides. So 1 over sine x becomes sine x over 1, which is just sine x. And then on this side, I have negative 1/3. So now I can look at it and say, hey, this is not so bad. This is kind of like the previous example. I just got to look at this and decide, is that anything from a special triangle? And so the answer is special triangle. No, it isn't. So I'm going to do the old trick of, I'm going to hit it with a sine inverse. So here we go with good old sine inverse. And let's see what sine inverse spits out. It spits out negative 0.34. And what I'm now going to do is I'm going to give myself a little drawing, because with sine, we can't use the plus pi, n times pi trick. And we know there's going to be a second one. So just run out of room here. Maybe I can squeeze it down here. Okay, let's draw what the cast rule and what the calculator has given us. Okay, first of all, this is a sign that is negative. So we would like to be here and here. And what has the calculator done? It spat out the angle negative 0.34. So we're rotating in the negative direction a little bit. So we're down here somewhere. Okay, I'm going to build that same reference angle in the other desired quadrant. And now I'm going to name these two angles in a slightly better way. So the first one here is, it's going to be pi plus our little reference angle. So one of them is just pi plus 0.34. And that turns out to be 3.48. And then the other one is going to be 2 pi, and we're going to back it up by our reference angle. So 2 pi minus 0.34, and that's going to give us 5.94. Now these are my specific answers that range between 0 and 2 pi. If someone said, give us the general solution, so just going to fit that in up here, okay, it would look like this. I would have 3.48 and 5.94. And here's the difference. I'm going to tack on multiples of the period. Okay, and the period is 2 pi, because we're dealing with sine. And I don't have to go and adjust this at all. Because we just had sine x equals, there's no change to this. It's not getting compressed or expanded. Oh, I should also mention that n is an integer. And there it is. We are done. General solution and the specific solution. So that's where I'm going to stop with this. We'll talk to you later.